Yeah, here I will show how to create a package and how to add a C++ file into the source directory belonging to the package and how to set the CMake list file parameter and, and the package XML if necessary. So each time we work, we open up the main, we can say the main folder, the Visual Code Studio in Catkin Workspace. And if we want to create a package, yeah, there is a command for that, and it is pretty hard to remember all these names, and therefore there is an, an wiki page which is uploaded in Learn into the robot folder. And then there is the ROS tutorials, and the tutorials is quite good here because there is an example code which we can use here. Catkin create package is the command, package name, and the dependency is standard message ROS pi or ROS copy, ROS CPP. So I can copy that, and then I need to go to the source CDSRC always. In here we create the package always, and then I will call it turtle one, um, and I do that. Then you can see it is creating an XML file, a CMake list file, an include file, and a source. And in the source, we are going to have a file added. Before we do anything, we could check the basic is okay by doing a catkin make. So now we have confirmed the file structure with the package turtle is correct, the CMake list file and the package XML file is correct. Then we open this folder by clicking on it so the pointer here is pointing down, and then we use here new file, and then we give it a name. It could be square as the turtle are going to run into a square. And CPP for the type, and then it is opened. And to fill stuff in, yeah, we could use again the tutorial actually for a talker, just to have some code we can try to adjust so it will be behaving as a publisher for getting the turtle going around. So it is simple publisher subscriber in C++, and what I go for is the raw code which is here. Control Alt, Control C, and then copy paste it into here, and that's fine. But we need now to look in the CMake list file to add this specific source code so it can be compiled and executable. Yeah, so we have the tutorial publisher code copy it here, and then we need to add this specific source file in the make list file, and we need to go down quite long to line 136 and remove the hash sign and change the name to square CPP. And then we need to, in line 149, to include this target Catkin libraries, and that's actually what we need in this project here. Of course, it can be more complex if we, for instance, need to have other includes into it, but for now it is enough. And then we say Catkin make, and then we can try, and we have to say source well and set up dot bash, and then we can run it as ROS run, and then the packet name turtle one, and where turtle one. Yes, so it's actually the product name, packet name here 2 times, and of course I have not any ROS core running, so therefore it is failing to contact the master, but just to show that it is actually working. Now, then next step is to try to figure out how to control the turtle simulator by publications in the square, and that is of course a challenge to figure that out and get that working. If we start out here running the ROS core, I think, we have to start the ROS core. Now I want to show a little bit more, because we need to understand the topics which we are going to use. So new terminal, and then we can start the ROS core. Yes, and then in a new terminal is a wiki for it, and there is a opportunity to get it running. So here we have it, and then the third terminal. There is several commands now we could try to use to get a deeper understanding of the structure, message structure, topic structure, and it is worth to use this ROS cheat sheet now, I think, because we can have ROS message show uses package and packages. We can also have a ROS node list ping machine, ROS topic here, display bandwidth ROS topic echo, ROS topic hertz, the rate, list, and if we start with that, then we can, I'm quite sure here, see that what topics the turtle publish. ROS topic list. And the two first here is the standard ROS core out. And then we have the turtle command velocity, we have a color, and we have a pose. And to move it, it is worth to go with this topic. Yes. Then we are here going to publish data to the turtle sim. And we need to know the topics which the turtle sim subscribe to. And that is found in this ROS wiki about the turtle sim. And you can see here that subscribe topics is geometry message twist, and it publish pose. So what we need to do actually is to publish to this geometry twist to figure out how it works by seeing the types for the data. Then we can use the command ROS message show with this topic. But we can also read the text here, linear and angular command velocity for turtle X. The turtle will execute a velocity command for 1 second, then timeout. Twist linear X is a forward velocity. Twist linear Y is the strafe velocity, and twist angular is the angular velocity. So to move it forward, we need to publish to this data here, and to move it in a circle, we need to publish data to this variable here. Now, let's take it and here. Now, then let's take the twist. Then this is the giving us what we need. So twist, the last name here is what we can show, and we can see the geometry message library is used, and there is a linear part x, y, and z, and x is moving it forward and z is turning it around. And so our job is here in the square code here actually to send messages, write code which can assign to the variables here. So this one, yeah. So now we know the no. So we can try to use this shader publisher as a template for creating the turtle sim or turtle to move in a square. And it is, as we saw in the terminal, there is a geometric message twist, and that we have to include here as a library as well as the so we write there the geometry message ms gs slash cpes.ho. That is first thing. Next thing is to give it a name, and that could be square. And we need to have a handle, and we need to have a publisher reference, which is called Chatterpop. We could rename that as square. Oh, square pop. And then we have here to actually set in the twist and the geometry message. And it is going to refer to square. And then it's not square, sorry, it is the command cmd velocity, which is the topic for this from this type of message. And the number 1000 here is to make a kind of queue or something like that. Then we have a loop rate, that is fine. And then we will here have an object of the type referring to the type geometry ms twist, and the name of the object, it is an object here, it could be message semicolon. This here is actually our reference to the XYZ, and this one is not here any longer. So if I take this one here, Control X, and then put it in here, then it is still following you can say the template. And then we have to assign values actually to the linear X to have it running, and the info could be used, but this one is not appropriate any longer, as we are not streaming anything out. Hello World is not getting out. We are getting data out. No. So we have to assign now message and linear dot x equals to, for instance, 1. And then we can take these here, and then we can say y, and the y is 0. And next, this z is 0. And we can try that out first. And I don't think this one is relevant. We can we could actually use it as we could want to write it out on the console as well, so we could take this here. Let's see if that compiles, and this should be substituted to square, square, and we actually also should have the field MSG angular x equals 0. And 3 times copy of that. Y set 7. Let's see if it can compile. We need to go down here, cd, no, there's some faults here, and one thing is we need to have the geometry message in our make list and dependencies. It must be in here, and in the package list must also be here. Build depend and int tag here. So build export. Let's see if I really think it is the same here. So we can take a copy of that, and then we can say geometry, and we can take a copy of this also. and geometry message. Yes. So now we have added the geometry message here, and we have added the geometry message here in the package. And lastly, I have changed this to be more proper because it is a 64-bit value, and the specifier for that is float. So if I then say here Catkin make, then is built, and now we are going to try to test it. So I have to run my Rust core. If it is, yes, it is there, and then a new terminal, the turtle. Is here, and lastly the terminal which are going to execute this little code. So I have to go back here, and then I have to remember after Catkin make source develop set up dot is certain. That's it. Then rush run turtle one turtle one. I think the package name is the middle here. Let's see how that works. And it is actually sending out the integer. I have okay. The problem is that the topic is turtle command velocity, and this is running in a while loop, so it will run forever until we stop it. Of course, it should be removed to move in a square. And this is telling us the speed, and the speed is 0.1. And each time I do a Catkin make, I have to remember to source it. But I have also, sorry to go back here, I need manually here to use save. If I change anything in any of these files, it is not done by default. You need to use save or save all. And if I then run it here, then we can look on the turtle, and it is moving this pace or speed of 0.1. And then of course we have to stop it, and then we have to turn it, and then we have to turn it. So basically we could reuse this here 4 times. Very low practical. So we could say, okay, now I want to turn, so therefore I should stop it, and then I want to turn, and the turn is in radianer, and you know pi is 180 degree, and to turn, to make a square, we must turn 90 degree. So therefore we should now find out what is the half of pi, and we could low practically say pi is something like it's actually in old days 22 divided by 7, that is pi. and then it is multiplied by 0.5. That should be 90 degree in radianer. So let's try and compile that and see if it is turning. It is not moving, but we could let it move also by having that first, and then we can move again by 0.1. So remember to save cat make, and then remember to source, and then we run it here, and then we can look now on the turtle. You see here, now it is turning. So as we saw, the turtle was just moving in a spot, turning round and round. We need here to have the turtle to move in an, we can say, circle, part of a circle, approximately 90 degree. So how to do that? Yeah, the radian, the angular speed is radianer per second. So if we want to know the radians, then we need to have a time interval. And if we multiply the time to the speed, then we get the distance, or here the angle. So therefore I have added some piece of code. First of all, we need to have the time included. And there is an class, a time class belong to us, and T0 initial time. And then we have a loop here where we iterate, and that means we are moving small steps to turn. We publish velocity message, and this is taken from another example, so it is the message we are going to, and then we take the time, and then we take the difference between the two times, and we multiply by the velocity of 0.1 radian per second. Then we multiply by this ratio 180 divided by pi, approximately pi is 22 divided by 7. Then we get it in degree, and I say less than 90 degree. So there will of course be an uncertainty depending on how small this is. The smaller this one is, the better precision we will get. Let's see if it can compile. It compiles. We have to store it before we compile again. And here we have an we can say a delay, and that means it is new code compiling. Source it, and then we are going to run it, and let's see how this is doing. And it is not going as well as I thought, but it's quite, it was moving. It was actually turning here. So now I have added quite a lot of code here to get it working actually, because we have the velocity, But if you want to measure a given distance, then we need to have a time, because velocity is meter per second, or angular velocity is radians per second. So if we then have the time interval, then we also can multiply the velocity with the time difference, and then we have a small increase in the distance traveled. So therefore, we need to have a time, and the time is do we get from the system by this call here into a double t0 start time. Then we have the velocity set, and then we go into a loop here, and then I say I want to go one distance, and to be honest, I don't know what one is here in Turtle Sim world. And then I keep publishing in the loop here, so that means my parameters I have here is published. And then for each iteration through the loop, I get a new time, and that means I have a delta time here. Delta time times the velocity gives a current distance, and the spin once and sleep is so it's not running infinity fast, and this spin once is that I can use Control C to stop it, and then I print out on the console here the current distance, so we can follow it if we like. Then I reset my velocity, linear velocity, because now I want to turn. I publish again to clear that, and then I have the need again to get a reference time, because now I want to do the turn, and that means the circular speed or angular velocity is set very low, so I have a nice little resolution on, and then I say as long as the current angle is below 90, then I need to turn with a given velocity. And again here, the time difference times the radians per second gives the radians, and then I convert here to degrees, so I can use this, and the same as before, and then I print it out. And if you look here in the console, then you can see the calculations of the angles, and if we go very much up here, I suppose we eventually, no, we can't see the other one. Anyway, it confirms that it's very precise actually. And then we can look here what happened. It turns actually, and now it is, and then it has, we can say, to redo the first loop here again, and then redo this one again, and that means this kind of template for the square solution. It would be obvious to have a function called with these two loops in, one for moving linearly and one for moving angularly. But that is what we have to do to come through with the square. Next step is, of course, to go into the kinematic for the real robot, because there you have a real distance, and that must be taken into account, because then you have two wheel speeds and a right and left wheel, and it cannot, when it has to turn, it must be different speed on the inner wheel compared to the outer wheel. So that is the next episode here.